Let's get started. It's 4 o'clock by my watch. Welcome to Colloquium. For those registered, the papers are over there, so feel free to turn those into me after class. Today gives me great pleasure to introduce a friend and colleague and someone whose science I really enjoy and find very interesting, Dr. Patrick Rafter. Patrick comes to us from UC Irvine. He's currently an assistant researcher there at the Tech Carbon Cycle Laboratory. He primarily, in his role at UC Irvine, he's primarily working with stable isotopes, but also radiogenic isotopes, particularly carbon. Patrick got his bachelor's in environmental science and marine science at the Florida Institute of Technology. And then after that, he went on to do his PhD at Scripps Institute of Oceanography. Patrick worked with Chris Charles there, who some of you may know. And then after that, Patrick ended up doing a postdoc at Princeton, working with Danny Sigmund. And he was at the ground zero of when there was this sort of momentum associated with measurements of nitrogen isotopes in planktic foraminifera. So this is really, really cool stuff. I was starting my PhD at the time, and it kind of blew my mind because they measure nitrogen that is bound in the organic component within shells. Okay, so imagine a carbonate shell extracting the organic compounds that are kind of fused within that shell and measuring the nitrogen. But nitrogen is not the only thing that Patrick does. Patrick's research really touches upon multiple arrays of biogeochemistry in the marine realm. He has worked on radiocarbon, on nitrogen, on organic geochemistry, and really brings different sets of expertise to problems in paleoceanography. So without further ado, I'm going to introduce Patrick. And Patrick today is going to be talking about a paper that just came out recently, and it's really a massive compilation, probably the most comprehensive compilation of radiocarbon as we move from a glacial world into our current interglacial world. So with that, Patrick, take it away.
Thanks, Cal. Thanks all of you for coming today. If I seem spastic at all, it's because Cal and Jordan have dosed me with caffeine just like an hour ago. It was a very strong cup of coffee. So today we're going to be talking about deep sea radiocarbon over the last 25,000 years. I like to walk and might walk right in front, so I'll try not to. And so what you're seeing here is a cartoon view of the C14 ventilation age of the Atlantic on your left, Southern Ocean in the middle as a zonal average, and the Pacific Ocean on your right over time, right? So we have, this is today, these are ship-based measurements. This is a proxy-based Heinrich stadial. These are all proxy measurements of the C14 ventilation age. Okay, so this is the C14 age of the proxy, whatever we're measuring. It's going to be either a deep sea coral or a marine microfossil called a benthic foraminifera. And so C14 ventilation age is C14 age of that thing, the archive, and the contemporary atmosphere, which changes with time. We'll talk about that in a second. So there's two things you may have noticed about this cartoon. First is that the C14 ventilation age of the glacial ocean is much older than today. And I've sort of masked out the shallower depths because there's actually some sort of weird stuff going on, and we're really going to focus on the depths of the ocean that exchange with the surface and sort of ventilate the deepest parts of the ocean. Okay, so you've noticed, hopefully by now, the C14 ventilation age is older in the LGM, and it gets younger towards today. Second thing you may have noticed is that these end pieces are on the left side and on the right side are different sizes. This is, I hesitate to call it an innovation as much as it's just a way I wanted to make more intuitive the volume of the Atlantic versus the Pacific Ocean. So these are, the width of these end pieces are scaled to the volume of the Atlantic on your left and the Pacific on your right. And this is more of a personal mission of mine to just point out like just how big the Pacific is. It's most of the ocean. And it's also a difficult place to make measurements because it gets really deep, it's pretty acidic nowadays and so on. It's difficult to recover proxy records, but we're working on it. And I think that's it. The last thing to say here is thank all my co-authors. I have 12 co-authors. This paper, the study is my COVID baby. Some people learned how to make sourdough bread. Some people had real babies during COVID. I decided to bring together a bunch of friends and acquire all the published radiocarbon measurements and also make a few hundred more from a couple new sites because our lab didn't get shut down during COVID, fortunately for us. Okay, so we're going to return to this, but I just wanted to start with that kind of. Nope, I'm just going to click. Probably has to click on it. Yeah, there we go. So this is part of a study that came out at the end of last year. And what I'm doing here, this is basically my new album. My album dropped. I got to go on tour, make sure people hear the new stuff. I know you want to hear the old stuff, but the new stuff is good too. You can see it here. There's a couple different ways you can get at it. Last item on our agenda in the beginning of this talk is a quick advertisement for this program I developed called First Gen Bees, First Generation Becoming an Earth and Environmental Scientist. So this is a program that I developed for high school students, local sort of Orange County, California, and San Diego County high school students who, like me, were first in their family to go to college. And so we bring them on campus, we do some fun stuff. It's not that difficult, actually. It's quite a simple model. I just want to advertise it. If anyone is interested in doing something like that here, it's not that much work, and NSF loves it. So win-win, right? Plus the kids, really cool kids. I've met some really incredible people through this program. Okay, so let's get on to the science. Who cares? That was a question. No, I'm just kidding. When I was in college, my advisor, before I would start talking about any data or anything, he would just say, hold up. Why should I care? Tell me why. So I figured I'd start my talk here. Why should you care about radiocarbon in the deep sea over the last 25,000 years? Well, first off, radiocarbon, or C14, as shown here, is a quote, most useful tracer of ocean circulation and ventilation. This is by this unknown scientist named Wally Broker back in the 50s. And so what do I mean by ventilation? I think a good analogy for this is the ocean. It can breathe in and it can breathe out. It can even hold its breath after it's breathed in. What's it breathing in? The atmosphere. And one of the things it can breathe in through a variety of ways. It's not just simply air-sea gas exchange, but it can breathe in atmospheric CO2. And if it holds its breath long enough, it can lower that atmospheric CO2, send us into an ice age. At least this was essentially the paradigm for explaining the late Pleistocene ice ages for decades now. We're still working on exactly the mechanisms, why it happens, when, and so on. But this has kind of been the paradigm for, like I said, decades. However, actually, these are all friends. These are smart, good people. During COVID, once again, during COVID, these fellas, they independently came to the conclusion that essentially we didn't need to have any change in ocean circulation or a change in the ventilation driven by ocean circulation to explain the proxy records that we have for the late Pleistocene ice ages. So independently, model results sort of testing this, and they even point out that the C14 proxy does not clearly support a more sluggish ocean circulation. Okay, so essentially what they're saying is we don't need a change in deep sea circulation to explain a huge change in global climate. So that would be phenomenal. This is also very provocative insight to how the climate system works, right? That you could have a global ice age and the ocean's just doing, the movement of the ocean is just essentially doing what it's doing. But that you could have some changes in the air, in how the ocean is exchanging with the atmosphere is what they suggested here. They call it changes. They call it disequilibrium. Okay, so this is sort of the argument that we want to directly confront with data. All right, and what is that data? This data is a new fossil radiocarbon compilation. I'm not the first to do it. I'm just the latest. I could show you the differences, but from the other studies, but it's essentially, we have essentially doubled the number of sites in this study. The last study was 2017, I think. We have increased the sites notably, and then in this study, so the colors represent the contributions from each study. So the new study, this study is the red circles, and then the red diamonds are actually brand new measurements, new sites that we worked on for this study. So, so that's what we're going to use to address this. And I'd like to give a quick preview of the results, just so you get the results twice. So you really get them, or you might leave, or you might fall asleep. You know, I get it. The question is, was there a change in deep sea ventilation over the past 25,000 years? And or exactly, you know, what exactly do we see with this new data set? And what we see is can be summarized as slower, lower, and it's all over. What I mean by that, well, there's some road signs. I thought that was fun. The question is slower. Was overturning slower? The answer is comparing the deepest southern and Pacific radiocarbon ages over this time scale, we clearly identify a slowdown in overturning. I think it's probably, it's being shown here first in our conclusions because it's our strongest conclusion. Was circulation different? I'm just going to walk a little so less boring for you. Was circulation different? We think it was. I think it's actually quite clear that circulation must have been different because the Pacific Ocean essentially flipped with respect to radiocarbon. And Pacific Ocean is essentially the ocean. It's so huge. So if you're doing that, then you're definitely having a change in what some physical oceanographers call the geometry of ocean overturning in some way. It may suggest the onset of a North Pacific deep water formation. Although I'm happy to have that conversation. Finally, it's all over. What do I mean by that? So if we're at this glacial state, that's different than today. And so it must have some change into what we're observing today. When does that stop? And interestingly, what we find is that this deep sea C14 ventilation age is essentially equivalent to what we see today, quite early into the deglaciation. So it's about halfway through the deglaciation. We have another 50 ppm of rise in atmospheric CO2 to occur after these changes in global ocean overturning and circulation have ceased. So we're at modern conditions. So it suggests that we have to look somewhere else for that extra, 40 to 50 ppm to explain that extra 40 to 50 ppm of atmospheric CO2 change. Okay, so that's the summary. We'll get back to it. I'm going to show you data to support all those statements now. But first, we got to give you a little tutorial on radiocarbon. So I haven't given this talk to a non-paleo audience in a while. I updated all my plots. So the x-axis calendar age is going forward in time to the right. And I wanted to point that out, and I hope you appreciate that. Because I did the work. I really want you to not be confused about simple things like that, and just get to the data. There are some initials here. It's Heinrich Stadial 2. It's approximately where that's happening. Last glacial maximum. Sorry, it's tiny. Heinrich Stadial 1, Bowling Allerod, Younger Dries. This is for like the real nerds. We can even put in bars to show what we're showing there if you want, but that's just for as like a second level piece of information there. So what are we looking at? We're looking at radiocarbon in the atmosphere over the last 25,000 years. All right, like I said, the x-axis goes back 25,000 years. We see a lot of variability. This is called the INCAL 20 data set. It's a compilation of measurements put together from tree rings, C14, and leaves found in sediment cores where they have a pretty good idea of how old the sediment cores are and so on. Things that grew into the atmosphere, so the recording atmosphere of C14. Okay, so there's a bit of variability. It can be a little confusing, so I'm just going to walk you through this a little bit. C14 is the radioactive isotope of carbon produced in the atmosphere. So that's why this is important. Now, interpreting C14 is where it gets a little sketchy, I think, for at least for me before I was in this world, even as an isotope geochemist, a trained isotope geochemist, it gets a little wonky. So we use different ways to interpret different notation. We're showing delta C14 notation here, but we will also refer to it as a C14 age. Let's talk about like how these things relate to each other. So, for example, if C14 is being produced in the atmosphere, which was said by essentially started by cosmic rays coming in and smashing nitrogen in the atmosphere. The length of time in the atmosphere since this radiocarbon has been produced or reacted or like interacted with the atmosphere, you would, if it's been a long time, you would see fewer C14 or a lower ratio of C14 to C, a lower delta C14 or an older C14 age. Okay, so that's sort of the terminology there. Now, it's a little shaded here, but I'm going to go, all I'm doing here is saying, okay, C14 age, how does this relate to delta C14? Well, I just took 1,000 C14 years off of the atmosphere, and so that's what that looks like. This is 2,000 years, this is 3,000 years. Okay, so that's 3,000 years older than the atmosphere at that time. Why that's useful and why that's important here is, well, let's take a look here. Let's just give something that has that was produced, back in the LGM, and then something that was produced down here in the Holocene. They both have the same delta C14 value, but this C14 age, which is the C14 age difference from the contemporary atmosphere, is very different. So that even though they might have the same delta C14 value, the interpretation of the environment that thing, that archive lived in, is going to be very different, right? This is a much older C14 ventilation age than we're seeing during the Holocene. Now in the ocean, this provides information on circulation, especially overturning. I'm going to show you that in a second, but simply put, the ocean communicates with the atmosphere in sort of some limited environments, and then comes deeper water. So it's carrying that signal of the atmosphere into the deeper ocean. And you can think of it as it's radioactive, right? So as soon as it stops interacting with the atmosphere, then you're starting this radioactive clock. And that clock will get older, provide an older C14 ventilation age as it's removed from the atmosphere. I hope that works. I've been trying to do this talk for a couple of years now to try to educate people about radiocarbon, how useful it is, how to interpret it. So, just to really spell it out here, a slower ocean overturning, should expect reduced ventilation, slower ventilation, increased C14 age. That's how these go together. Okay, and then ultimately, this will result in an increase in the storage of carbon. Remember, it's the ocean breathing in, breathing out. It's holding its breath. It's holding the radiocarbon, the carbon that it's taken up. Plus, you have the biological pump. You have phytoplankton producing, converting surface water carbon, biomass, sinks down, gets remineralized at depth. And if those waters at depth are slowly returning to the surface, you're going to keep it down there. This is all part of this scheme for connecting circulation, ocean physics to atmospheric greenhouse gases. All right, so you saw this before. This is what the modern ocean looks like. Remember the Atlantic on your left, the Southern in the middle, Pacific on your right. These are ship-based measurements. This is pre-industrial, so this is before the, I've filtered the data set to remove radiocarbon values that suggest they've been influenced by the atmospheric weapons testing, thermonuclear weapons, which increased atmospheric values to like 1,000 per mil in delta C14. So here we have the ocean. One thing to point out is where's the oldest C14 ages today? It's not the bottom of the ocean, it's at the mid-depth Pacific Ocean. So something pushing around 2,000 years, this C14 ventilation age. That should be important here. Now, why is that the oldest water in the ocean? Well, it's part of this overturning scheme. So these are this upper and lower cells of ocean overturning. So the upper cell is the formation of North Atlantic deep water in the North Atlantic. These push their way all the way to the seaboard in the North Atlantic. They move south. They join with other Southern Ocean waters. Some of these waters upwell and become even denser, become the most dense waters on the planet. And so some of that sort of penetrates a little bit into the Atlantic, but the return of these waters that initially started in the surface Atlantic, the return of these waters to the shallower depths is in the Pacific. And so this is a dashed line because this is a slow return. It's a diagonal return to the, so it's across density surfaces. It's a slow exchange, in other words. And so what this means is these waters last really saw the atmosphere when they were in the North Atlantic. They come up to the Southern Ocean. Maybe they get a brief delay. They barely catch their breath, change very little, and then they go down again. It's really holding its breath now, and the C14 age is getting very old. Okay, that's how it works today. One way to break these down, sort of a framework in which to interpret these seawater measurements and eventually the proxy measurements, is to think about them on neutral density surfaces. So these are density surfaces on which that mixing these currents are going to work. And so I've chosen these values based on Lynn Talley and Veronica Kems's work. Great work. Okay, so that's today. Now, how do we get in the past? We're going to use these marine proxy records. All right, so marine microfossil, this should say deep sea coral record as well. So what I'm showing here is a simple fidelity test. Like, okay, let's just say I've convinced you, you care. And okay, and then you say, okay, well, now prove to me that you can do what you say you're going to do. So what we have here is this C14 ventilation age on the y-axis. This is the proxy-based, and these are all the data in the global ocean over the last 4,000 years. And on the x-axis is this dissolved inorganic carbon C14 ventilation age. So that is seawater. That's a ship-based measurement. And so basically what I'm looking for is it 1-to-1? And so yes, slope is about 1. Actually, for this this time series, for this time period, 0.97, pretty good. It gives an error of about plus or minus 100 years. But as you can see, there are some that are easily plus or minus 250 years. So I would say for any individual, any single observation, you'll have a pretty big error. But that really, in my mind, motivates the use of a lot more data. And so that's exactly where I'm moving both with this data set and in the future. We're just cranking out measurements here to try to beat down this error that, what does it come from? You could ask, we could talk more about like why we might have some of these values that go way off the 1-to-1 line. But gets into the real nerdy stuff. One nice thing here is there's a lot of assumptions that go into figuring out what the calendar age is. So we have to know where we are in time as well to kind of difference it from the atmosphere. So that's one of these probably sources of errors. And so the legend here shows the different sort of strategies for establishing this calendar age. There are a lot of strategies, as you might suspect. I kind of ordered them in the order of most trustworthy to more, well, I wouldn't say less trustworthy, but I'm more skeptical about. And yet, there's no clear bias in any of these. That's kind of nice too. Okay, well, what about different time slice? So here's the past 6,000 years, 4,000, 2,000, and 1,000 years. We all get about slope of 1. There's nothing notable about that. As you go further back in time, you might suspect, actually, I haven't looked at it in a while, like 8,000, 10,000 years. It's possible, maybe probable that this comparison is not something that not appropriate. That the modern ship-based measurements may not be exactly reflecting 10 to 8,000 years ago water, but I should say they all pretty much fall together as well. Okay, so we've established, let's just assume we've established you care. Let's assume that we've established you believe the proxy. Okay, now let's take a look at the cartoon again. I think I made this one slower. think for dramatic purposes, I forget why, than the first one. But you could see, oh, well, I can talk you through it easier. These browns, much older. We're going into the deglaciation. This is midway through the deglaciation. And then here's the day. And so not very different. That's part of one of our conclusions. So that's, I should say that this cartoon and this way of looking at it at the data set as a zonal average is fun, but it's kind of, if you've ever met a paleoceanographer, we love wiggles. And so I spent most of COVID figuring out the best way to do this. Happy to talk about the details of this, but what we did here was we said, okay, well, let me explain the data first. Okay, Atlantic is all on your left, Southern in the middle, Pacific on your right, as before. The top row is the data in delta C14 notation. The bottom row is the data as a C14 ventilation age. And the gray line, remember, is the atmosphere. So in Cal 20. So the bottom row is the difference between the data and the contemporary atmosphere, right? Just to remind you. We're showing two lines in each box. And the dotted line is this mid-depth, or like the upper cell of the global ocean overturning. And the solid line is the lower cell. So the deepest sites we can find in any ocean basins. And so there's some interesting differences there, right? Let's go into those differences. So we're just going to talk about C14 ventilation age. I've intuited that this is more intuitive to audiences than the delta notation. Older ages means, being around longer, essentially. Okay, so Atlantic, and once again, time is moving forward to the right. I haven't noticed any errors yet, which is good. Like I said, I did this late last night. Here's some details on the data set. Again, just sort of like the boundary over which we're looking at the data. We cut it off at 60 north. We're calling the Southern Ocean everything south of 40 south. That's probably, we did a variety of sensitivity tests for constructing these. And I would say actually the thing that's most that these curves are most sensitive to is where we choose this boundary. If we choose it too far up, like 35 south or 30 south, really get into waters that are clearly different than the Southern Ocean waters. 40 south seems to be right. We use Loess. Actually, an important constraint here on the data set is we're excluding 3 sigma outliers. There are a few outliers here. Some sites that, I don't know, maybe they're showing the influence of carbon that has no C14 in it. It's an open question. So we just, if we took a 500-year bin of all the data, and if anything fell more than 3 sigma outside of that average bin for that basin and those density sources, they're out. All right, and there's this depth bias correction as well. If we had all our sites were in the deepest part of a basin, they're necessarily going to say it's older there, right, than everywhere else. But so we do a minor correction there. Actually, it's pretty minor. It's a minor adjustment to the data set, actually. All right, so we're back to our questions. Slower. Was overturning slower? We're simply going to look during the last glacial maximum. We're going to compare the Southern Ocean, the deepest Southern Ocean, with this downstream water in the Pacific Ocean. So that's the question. And so we're just simply going to look at these two sites for this part of the records, this last glacial maximum. We're going to bring them together. All right, C14 ventilation age. Southern Ocean's up here, right? Got a little younger C14 ventilation age. The Pacific way down here, really old on average, 3,000 years, so 1,000 years older than the oldest waters we see today. What's it look like today based on seawater measurements? This difference between these sites, between these deep waters, 550 years. By the way, if we look at the proxy data for the mid to late Holocene, 550 years, that's pretty nice. Bigger error, as you might expect. That's cool. That's a kind of nice, another fidelity test, another test of the data. All right, what about the last glacial maximum? The difference between these two, the Southern and the Pacific, 850 years. Okay, so it was overturning slower. Yeah, at least by this metric, 300 C14 years slower. Now, what does that mean for actual spare drifts and transport? Great question. I've asked a few people to help me with that, and we are working on it. But we can say we at least have the sign, right? Like it was lower. I think it's something like 15 spare drifts today. I wish I could say this. I wish I could put a number on this, but we're working on it. Okay, lower. What do we mean by that? Was circulation different? To address this question, we're going to look only at the Pacific Ocean, but we're going to consider the shallower, the mid-depth deep waters and the bottom deep waters. I don't know if those names work best. I mean, we workshop the hell out of calling it mid-depth or bottom, or some people wanted me to call it intermediate. It's not intermediate depth. Anyway, we're going to call it mid-depth, which in the Pacific is something like 1,000 to 2,000 meters, and the bottom water is everything below that. Okay, so all right, what do we see here? So the last 25,000 years, the oldest C14 ages are at the bottom, at Pacific bottom waters for most of the past 25,000 years. All right, this is flipped relative to today, right? The oldest C14 ventilation age of the Pacific anywhere in the ocean today is not at the bottom waters, in these mid-depth waters. So the symbols over here are actually showing and the error bars are actually smaller than the symbols. But the oldest waters are at for the mid-depth today by a couple hundred years. It's not huge. So this says that during the LGM, not only was there a flip in the Pacific Ocean, which is most of the deep sea, but it flipped and the difference was huge. All right, so this is consistent with a reduction in the exchange between these two cells, the lower cell of the ocean overturning and this upper cell, which is the return of the ocean overturning. It's basically the last step for the ocean to breathe out. Okay, we could look at this in a different way. And so I was taught to call this a paleo CTV. This is taking our proxy data and saying, well, okay, for a certain period of time, what would, like, if we were able to drop a CTV, everyone know what a CTV is, a way to like sample water in the middle of the ocean, bring it up and measure it. So if we were able to do this during the last glacial maximum, what might we find? Okay, so what we're comparing here is the black line with the gray envelope is seawater ship-based measurements today. So that's what C14 ventilation age looks like for the Pacific Ocean today. And so the circles are all the proxy data for the last glacial maximum, that's LGM. And then this line here is the lowest smoothing for that data. And so what you can see is they're pretty different. Well, the mid-depth, I can put the lines here. So the mid-depth, actually the mid-depth is more like 1,000 to 2,500 meters. But for that depth range, the paleo CTD suggests a C14 ventilation age for the Pacific mid-depth that is essentially no different than today, which is surprising. Everywhere else in the global ocean is older, but this one place essentially the same as today. Interesting, right? I think. Below that, Pacific bottom waters, it's older during the last glacial maximum, as we pointed out before, but you can see this sort of what the trend looks like with that. Okay, so let's compare that. This is the only other proxy you're going to have to think about here. But it's another carbon isotope, it's the stable carbon isotope. And so we're comparing, it's another paleo CTD, right? So the seawater C13 is the black line with the gray envelope, and the paleo CTD of C13 is the same. It's the circles with the brown line is showing the lowest smoothing of those depths. So sorry, there's we've collected a couple. Sorry, this is a new compilation plus some new measurements we made from Wanda Puka Ridge. Ridge or Rise? What was that? Is Ridge? Okay. I mean, I don't know if you're like me, but my first thought was like, wow, it's like sort of mirroring each other. Interesting, right? Completely independent data sets. But when we find the oldest C14 ventilation ages, we're finding the lowest C13. And so this is fairly easily linked together, right? So the oceans, remember, it's holding its breath, I told you, are a little bit longer than usual. but we're still having the phytoplankton fixing carbon in the surface ocean. Their corpses are sinking to death, remineralizing. As they remineralize with depth, CO2 is being released and nutrients as well, right? So what essentially we're having here is a slowdown in the overturning circulation. It's allowing more of the phytoplankton corpses that are now CO2 and nutrients to build up at depth. The explanation, the link between C13 and nutrients is that these phytoplankton have this very distinctive low C13 value. So they're going to kind of pull it to the left here. So different than we're seeing today, right? The black line is today. So that's cool. That's super cool. So our paleo C13 CTD is also showing it's flipped relative to today. One other thing you might notice is actually the shallower, the mid-depth C13 is sort of crosses over what it looks like today. It's not like the C14 at the mid-depth looks pretty similar. The C13 looks like it has a completely different configuration. We think that says something about the formation of North Pacific deep water. This would be consistent with some waters that used to be at the surface, have a higher C13, that are sort of only penetrating to about this depth. And so a couple papers have suggested that before. This would also be consistent with the fact that everywhere in the global deep sea has an older C14 ventilation age except these waters. And that could be brought about by, well, you're bringing surface waters in that are going to be very young. They've exchanged with the atmosphere. But then they have to mix with the oldest waters on the planet. So you end up with something that's not much older than today. So pretty cool evidence, I think.
Was that for the entire Pacific, Patrick?
That is for the entire Pacific. Yeah. And so I should say, thank you for prompting me there. That's how little data we have. We actually have to take the entire Pacific north of 40 south, which is, if you've ever worked with like a seawater based data set where you can go out and make measurements, that's a lot of ocean to average, but that's how few data points we have. And actually one of my sort of mid-career goals is this was step number one. Step number two is to keep building more of these records and start getting to look at more regional signals and how they differ. But yeah, this is the whole Pacific. What's circulation different? Essentially, was the geometry of ocean circulation different? Yeah, man. The oldest ages in the largest ocean on the planet are totally flipped from today. And I think that clearly speaks to some change in ocean circulation. And in fact, there's some modeling results that tested this in sort of a roundabout way. And the only way they could find where you change where the oldest ages of the deep sea was by changing, not by changing the rate of overturning, but by changing the surface water buoyancy gain and lost in the Southern Ocean. That's just a very different, we can go into details if you want, but this is also a great paper for that. It's essentially a way to change this geometry of the overturning, not necessarily just the rate. Okay, so it's all over. What do we mean by that? When does it stop changing? Now, that was out of order. Now, a really simple cartoon. We're going to cycle between the bowling alley rod, which was 14.7, 12,000 years ago, and the pre-industrial, so the ship-based. Proxy-based, ship-based. This is sort of a qualitative way of looking at the data set and saying, yeah, they look pretty similar, actually. So we do that, and then we say, okay, let's actually look at the data more quantitatively, but in a very simple way. And what we find is, so the symbols here on the right are averages for each water mass, density service, and basin today. And so what you see is a rapid rise up, and around 14,000 years ago, around that time, the bowling alley rod, all the waters are pretty damn close to what they are today. So the Atlantic has sort of a blip up and then it gets up maybe a little later. Southern Ocean is clearly there. It actually overshoots where we are today. So here's Southern Ocean today. There's a clear overshoot, which some have suggested it is a response to more the North Atlantic deep water formation coming on and just going overboard. And then you're here in the Pacific, they both get up to speed by about 14K. There's some more variability. The error bars also blow up there because we start to lose data in the Holocene. And I understand why. The radiocarbon measurements are expensive if you don't live in a radiocarbon lab like I do. And the Holocene is less interesting, so people are less likely to build those data sets. But we should work on that, and that's another thing. What else do I have here? Okay, so this suggests that midway through this glaciation, this transition from global ice age to the current warm period, only midway through there, that ocean circulation is essentially the same thing. So that suggests that we need to find something else, some other way to explain the continued rise of atmospheric CO2. So this is something like, this is going from like 180 ppm to 230 or 240 ppm at this time. We still have quite a bit to go to 280. All right, so when does it stop changing? It appears to stop changing somewhere around midway through the deglaciation. All right, so you guys made it to the end. I'm 41 minutes in, so that's not so bad. Another thing we did with this compilation that was a little different, I think, than others is, well, let me just say, when you're work with compiling other people's data, let's just say that you get a full paper out of it. Some people might just have bad feelings about that. And I may be saying this from experience, but I've definitely seen it. I'm the compiler, by the way. I did not want that to happen. It was another kind of COVID epiphany where, well, the first COVID epiphany was I only want to work with people I like. And as many people as possible, which is why there are 13 authors on this paper. I would have added you, Cal, but you're kind of.
It's all right.
I don't know why I didn't. Next time.
That's
You're definitely worthy. You're worthy. I think we got to 13. Or like 13. Just stay there. Okay, back to the data set. So we made the whole compilation available both at NOAA's paleoclimate their server and this Pangea as well. And as you can see, there's way more authors on this data set. It's every first author from every published study. And the reason why I'm highlighting this is because it took me a whole day to just to get all their names up there and convince Pangea to do this. They were fine with it. But what this means is if someone uses this data set in the future, then all the first authors are going to get a citation for that. So that's kind of nice. Finally, just want to thank all of our funding sources. And that's it. Although we can talk more if you want. Okay.